Good afternoon. So today we shall discuss the concept of quantum state of an electron. As I have said earlier, that every electron in an atom has its unique set of all the four quantum numbers such as n, l, ml and ms. N is the principal quantum number, l is orbital quantum number, ml is orbital magnetic quantum number and ms is the spin magnetic quantum number. So for every electron in an atom, the values of these four quantum numbers is said to constitute a unique set. For two electrons belonging to the same atoms will not have same values of all the four quantum numbers. This set of quantum numbers specifies the state of an electron in an atom, and this is called as the quantum state of an electron. That is called as quantum state of an electron. The number of electrons, the number of quantum states for a particular value of L, the orbital quantum number, can be obtained like this. For that purpose, let us consider the example of oxygen. For oxygen, we know that the atomic number is 8, Z is equal to 8. For oxygen, the atomic number is 8, which indicates that there are 8 electrons in oxygen atom. Let us try to write down the values of these four quantum numbers for every electron belonging to the oxygen. So for first two electrons, in S subshell of K shell, for which the principal quantum number n is equal to 1. So the first electron has the quantum numbers n equal to 1, l equal to 0, ml equal to 0 and ms equal to plus 1. And for the second electron in oxygen, n is equal to 1, l equal to 0, ml equal to 0 and ms equal to minus 1. So these two sets of quantum numbers are found to be different from one another for the two electrons in S subshell of K shell. Though the values of N, L, Ml are same, same for both the electrons, the values of ms are going to be different. Then, so we can say that these are the non-identical sets of the quantum numbers. Next two electrons. Next two electrons enter in S subshell of L shell. And for L shell, the value of L, the replacement quantum number, is 2. So that we can write the 4 quantum numbers for the 2 electrons in S subshell of L shell. For the third electron, the principal quantum numbers will be N equal to 2, L equal to 0, Ml equal to 0, and Ms will be equal to plus half. And for the fourth electron, N will be equal to 2, L is equal to 0, Ml equal to 0, and Ms equal to minus half. So again, these two sets are different. They are non-identical. Then, out of 8 electrons, 2 electrons enter into S subshell of K shell, 2 electrons enter into S subshell of L shell, and still there are 4 electrons remaining. So these remaining 4 electrons enter into the P subshell of L shell. Remaining 4 electrons enter into P subshell of L shell. For L shell, we are saying L is equal to 2. So, for L is equal to 1, Ml is equal to 0. For L is equal to 1, Ml can have the values -1, 0, and +1. So the values of Ml varies from -10 to +10. So when L is equal to 1, Ml can take the values -1, 0, and +1. So that for each value of Ml, Ms can be plus half and minus half. For each value of Ml, Ms can have two values, either plus half or minus half. So the maximum number of electrons that can be accommodated in 2p subshell of L shell will be equal to 6. But for oxygen, in all there are 8 electrons, out of which the 2 electrons are accommodated in 1s level of K shell, 2 electrons are accommodated in 2s subshell of L shell, and there are only 4 electrons left. There are 6 vacant places, but only 4 electrons are left. So all the 2p subshells in this L shell will not be completely filled. So let us see what will be the values of 4 quantum numbers for the remaining 4 electrons. Fifth electron will have the values N equal to 2, L equal to 1, Ml is equal to -1 and Ms is equal to +1. For the sixth electron, N is equal to 2, L equal to 1, Ml equal to -1 and Ms is equal to -1. Then for the seventh electron, N is equal to 2, L is equal to 1 only, Ml is equal to 0 and Ms is equal to +1. And for the eighth electron, N is 2, L is 1, Ml is equal to +1 and Ms is equal to +1. So for Ml equal to 0, Ms equal to -half, and for Ml equal to +1, Ms is equal to -half. These two positions of electron are vacant. So this 2p subshell is not completely filled. It is not completely filled. So that the orbital magnetic moment and the spin moment becomes 0. So that is how we can write the quantum states of an electron for all the electrons belonging to a particular atom. Next we shall see is the spectral notations of quantum state. Spectral notations of the quantum state. For writing the atomic states, it is necessary to know the orbital angular momentum, that is capital L, orbital angular momentum and spin angular momentum S. So whenever we want to write the atomic state, it is must that we should have the knowledge about the orbital angular momentum and the spin angular momentum, such that the total angular momentum can be obtained. J is the total angular momentum. This total angular momentum J of an atom is the vector sum of the orbital and spin angular momentum of an atom, so that we can express the total angular momentum J bar is equal to the vector sum of the orbital angular momentum and the spin angular momentum, that is L bar plus S bar is equal to J bar, where L bar is nothing but equal to summation of Li bar, and it gives the orbital angular momentum for an atom, and it is equal to the vector sum of the orbital angular momentum vectors for all the electrons belonging to a particular atom. Similarly, S bar is nothing but equal to summation Si bar, where this S is small, correct? You can say this is summation Si bar, where this S bar represents the spin angular momentum for an atom, and it is expressed as the sum of the angular momentum of each individual electrons belonging to the given atom. In addition to this, the total orbital momentum of an electron L bar and the total spin S bar gives the total momentum G bar. The sum of L bar and S bar is going to give the total momentum G bar for an atom. And this type of coupling between L bar vector and S bar vector is called as LS coupling. It is called as LS coupling, or it is sometimes also called as Russell-Saunders coupling. It is sometimes also called as Russell-Saunders coupling. The total angular momentum vector G bar is found to be characterized by the total angular momentum quantum number G, and the total angular momentum J bar is also found to be quantized. So, in accordance with the quantum condition, we get J bar is equal to under root J into J plus 1 and H upon 2 pi. So this is how we can obtain the value of J bar. The total angular momentum of an atom is decided by the last unpaired electrons in an atom, so that the core of electrons in an atom do not contribute to the total angular momentum J bar of the atom. So the total number of allowed values of J bar for the given L bar and S bar can be expressed like this: J is equal to L plus S minus 1 and so on, L minus S plus 1, and is values of L minus S, which is small. So, for example, for the value of L is equal to 3, for the value of L is equal to 3, it is observed that, and the value of S is equal to 3 by 2. So if L is equal to 3 and S is equal to 3 by 2, then we get the values of C as 9 by 2, 7 by 2, 5 by 2 and 3 by 2. We get the values of J as 9 by 2, 7 by 2, 5 by 2 and 3 by 2. So there are 4 values of J bar given by this 9 by 2, 5 by 2, 7 by 2, 5 by 2 and 3 by 2. So there are twice s plus 1 different values of J bar, and each value of J bar is going to give the separate atomic state. Each value of J is going to give the separate atomic state, and this shows that there are twice s plus 1 different energy states for the given atom. So the quantity twice s plus 1 is called the multiplicity of the atomic state. The value twice s plus 1 is called as the multiplicity of the atomic state. So we can obtain the multiplicity for the atomic state like this. For twice s plus 1 is equal to 1 represents the singlet energy level. That is S is equal to 0. Then twice S plus 1 equal to 2. It represents doublet energy level. That is S is equal to 1. Sorry, 1. S is equal to half, and twice S plus 1 equal to 3 represents triplet energy. And for this S is equal to 1. So if we substitute S is equal to 0 here, we get twice S plus 1 is equal to 1. If we substitute s is equal to 1 half here, we get twice s plus 1 is equal to 2. And if we substitute s is equal to 1 here, we get twice s plus 1 is equal to 3. So, in accordance with what is the value of s, we have the singlet energy level, doublet energy level, or triplet energy level. So, that is how we can obtain the energy states of the electrons. Here, we should remember that if the value of L is less than S, if the value of L is less than or equal to S, then the number of values of J, is going to be given by twice L plus 1. So if the value of L is less than or equal to S, then the number of values of J are given by twice L plus 1. So that is how we can find out the different energy state or the energy levels for the given atom. These atomic states are going to be represented by the different notations. Atomic states are denoted by the capital letters S, P, D, F, G, etc., which correspond to the values of L equal to 0, 1, 2, 3, 4, etc. respectively. These atomic states corresponds to the values of L equal to 0, 1, 2, 3, 4, etc. respectively. So, for L, here the atomic state is denoted by using the term symbol as twice s plus 1 Lg. Here, twice s plus 1 is called multiplicity. Is called multiplicity, and S is equal to summation Sj. It represents the spin momentum of the atom. It represents the spin momentum of the atom. So, the values of L resultant orbital angular momentum of the atom. So, this L equal to 0 represents S state, L equal to 1 represents P state, L equal to 2 represents D state, L equal to 3 represents F state, and so on. So that is how we represent the different atomic states of the atom. Now, if we consider the example of oxygen, if we consider, not oxygen, it is the hydrogen. If we consider the example of hydrogen, for hydrogen, as we know that there is only one electron, and if that electron exists in the ground state, if we have a hydrogen atom in the ground state, the principal quantum number N is 1, orbital quantum number L is 0, the orbital magnetic quantum number Mn is 0, and the spin magnetic moment Ms is equal to plus 1. So, the state of an atom, therefore, state of hydrogen atom can be expressed as, that is, twice S plus 1 Lg can be expressed as twice S1. So here, this superscript 2 gives the multiplicity symbol. Superscript 2 gives the multiplicity symbol for L is equal to 0, and the subscript 1/2 stands for the value of G. Stands for the value of G, the total momentum. So this is read as doublet S12. This is read as doublet S12. So let us consider another example. For L is equal to 3, for L is equal to 3 and S equal to half, the values of G are 7 by 2, 5 by 2, 3 by 2 and 1. These are the possible values of G for L is equal to 3 and S is equal to 1. So that the multiplicity that is twice S plus 1 works out to be equal to 7. So it works out to be equal to 7. So this is equal to this is equal to 2 into 1/2 plus 1 plus 2. So plus s plus 1 is equal to 7 indicates that this is equal to 2. So multiplicity is 1. So L is equal to 3 indicates F state. L is equal to 3 indicates the F state as so we can write the states as twice F, that is 7 by 2, 5 by 2, 3 by 2 and 1. So we can write these F states as twice F, 7 by 2, 5 by 2, 3 by 2 and 1. So all these states are going to be the doublets. All these states are going to be doublets. And the atomic state 2F7 by 2 can be written as doublet F7 halves. This can be written as doublet F7 halves or doublet F5 halves or doublet F3 halves or doublet F half. So like that we can read these different states. So that is about the spectral notations of the quantum states. And next we want to discuss is the spectra of single valence electron systems. That will continue in the next video. Okay. Thank you.